Hello everyone. We shall solve the remaining exercises of this section in this video. So beginning with exercise 1.2.14, express the following sentences using quantifiers. Negate each of them in plain English. Write the negation using quantifiers and compare the two. Okay, so these are statements involving multiple quantifiers. So the first one, there is a tree in this campus, all of whose leaves are green. So you can see that there is, that means existential quantifier is coming here. All of whose leaves, universal quantifier is also appearing, right? So first, let's say, since there are two quantifiers involved, there will be two set of contexts. So your first set of context is set of all trees. So let X be set of all trees in the campus. Okay, let X be set of all trees in the campus. So there exists a tree. That means in this set there is one element. So using quantifiers, how will you frame this sentence? There exists a point in this state. That means there is a tree. So there exists X in it. So X is a tree in the campus. Okay, for which the remaining things will happen. Now this tree X is picked up. So now I have to figure out another set of context. That is all leaves on this tree X. Okay, so there is a tree in the campus. This is done. All of whose leaves are green. So I need another set of context, set of all leaves of it. So that I will name Lx. So this is all leaves of the set, leaves of the tree X. Set of all leaves of the tree X. So there exists X in X. That means there is a tree in the campus, all of whose leaves. For all, you can choose any other variable now here. For all L in Lx. That means all of whose leaves, all the leaves of this tree, L is green, such that L is green. This is the property now, L is green. Okay, so you can see existential and universal quantifier. Now when you negate it, how it will look? For all X in X, X as we had seen earlier, the quantifiers get reversed. There exists L in Tx, sorry, L in Lx, such that L is not green. This is the negation using quantifier. And negation in plain English will be how now? Given any tree in the campus, there is a leaf on it which is not green. Given any tree in the campus, there is a leaf, there exists a leaf, or you can say it contains a leaf. I'll reframe it. Given any tree in the campus, it contains a leaf, at least one leaf is there, which is not. Okay, so this will be the negation of the given statement. So you can see that existential turns to universal and universal will turn to existential. This happens when you negate the statement. Now looking at question number B, every tree in this campus has at least one brown leaf. So again you'll see that there are two set of contexts. Your first set of context is X, set of all trees in the campus. Set of all trees in the campus is your first set of context. Now I will try to write this statement, let's call it A, using quantifier. Every tree in the campus, that means for all P in X. So P is a tree here. For all P in X, let's see what will happen. Has at least one brown leaf. So now I'll need another set of context, all leaves of the tree P. So LP will be all leaves of the tree P, because P is a tree, right? So there exists a leaf on this tree. So there exists one leaf. Okay, I'll call it maybe Z. So there exists a Z in set of leaves, that is LP, such that brown leaf they are talking, such that Z is brown. Correct? So what will be its negation? There is a tree. I'll negate the plain English statement first. There is a tree in the campus, all of whose leaves are brown. Right? No, it says at least one leaf is brown. You have to say that all of the leaves are not brown. They are non-brown. So there is a tree in the campus. There is a tree in the campus. All of whose leaves are non-brown. That means they are not brown. So you pick up any leaf of the tree there. There is at least one tree in which all the leaves are not brown. Correct? So using quantifiers, now what will be this? Again, as I said earlier, you will replace there exists. So there exists P in X such that for all Z in LP, Z is not brown or non-brown. This will be the negation using quantifier synthesis. I hope it is clear. Look at statement number C. In every shelf in the library, all books are mathematics books. That means if you pick up any shelf in the library, all the books in that will be mathematics. So basically, let's say this is your library, and these are the shelves. And in these shelves, there are books here. Right? So if I call this as statement number C, let's see, then what will be my set of context first? Set of all shelves in the library. So that I'll give letter capital. Set of all shelves in the library. So for all S in S, let's say, that means for S is the shelf now, small. For all shelves, now which is the second quantifier? All books are mathematics. Again for all. So in this shelf, I have to look out for BS. BS means all books in the shelf. All books in the shelf A. Small. Okay. So for all B in BS, that means given any books in the shelf, B is mathematics book. B is a mathematics. what will be its negation? Not C using quantifiers. There exists S in A such that there exists B in BA such that B is not a math. Okay. And now we have to write the negation using plain English again. So there exists a shelf in the library. At least one shelf in the library. And there is at least one non-math book which contains at least one non-math book, non-mathematics book. Okay, so both the in the original statement both the quantifiers were universal. So in the negation both the quantifiers will be existential as you can see. Now sentence B. Every tree in the campus has all of its leaves green. Again, both the quantifiers are universal here. So what will be your first set of context? Set of all trees in the campus. So let capital T be trees in the campus. So if I call this as statement number D, how will D look like? Every tree in this campus. So for all T in D, what will happen? All its leaves are green. So of this tree small t, I have to look at all leaves. So all the leaves of t. Set of all leaves of the tree small t. So for all L in LT, that means for all leaves of the tree small t, L is green. So both the quantifiers are universal. So what is expected in the negation? Both will turn to existential. So there is a tree in this campus which is small t, all of whose leaves are not green. There exists a tree such that there exists a leaf on this tree T such that L is not green. So using plain English now, what will be the negation? There is a tree in the campus. There is a tree in the campus which contains a non-green leaf, which has a leaf which is not green, which is not. Okay. And the last one, there is a shelf in the library in which there is a mathematics book. You can see now both the quantifiers are existential here. There is. So if I call this as statement number E, all the shelves in the library. So I'll call it S. Shelves in the library. So your E will look like there is. So there is S in it such that in the shelf I have to look out for books. So BS will be set of all books in the shelf. So there exists B in BA such that B is a math book. Okay, so now to negate this, I have to switch the quantifiers to universal. For all x in A, for all B in BA, B is not a math book. C is a non-mathematics book, right? So how will you frame this now? Every shelf in the library has all non-mathematics books. So in plain English, every shelf in the library has all non-mathematics. So all its books are, or you can say given any shelf in the library, it contains all non-mathematics, right? So that is done. Moving on to exercise 1.2.16. So what is your statement here? There exists an integer x in z such that for any y in z, we have x plus y is equal to 1. Write this in simple using quantifiers, negate it and write it in plain English. So the given statement, I'll call it statement number A. So using quantifiers, how will you write it? There exists an integer. So there exists x in z such that for any y in z, for all y in y, no matter what integer you take, x plus y will be equal to 1. So it's talking about existence of additive identity. So x is the zero additive identity here. So what will be its negation? For all x in z, no matter which integer you take, there is an integer y such that x plus y is not equal to 1. Okay. So for all x in z, there exists an integer y for which x plus y is not equal to 1. So what will be the negation in plain English? Given any integer x, given any integer x in z, okay, there exists integer y such that x plus y is not equal to y. Such that x plus y is not equal to y. That is the negation in plain. The last exercise, 1.2.17, that's the Archimedes property. For each x positive and y in R, we can find a natural number n such that nx is greater than y. We will write this in quantifiers. So if I call this statement a statement number, let's say P. So how will you write P using quantifiers? For all x positive and y in R, there exists a natural number n such that nx is greater than y. So what will be its negation? There exists a real number x positive and real number y such that no matter what real number, natural number you take, for all n in n, nx will never be greater than y. This will be the negation using quantifiers. And in plain English, how can you frame the negation? There exists a positive real number. There exists, I can say r plus actually instead of saying x greater than 0, and real number y. Y can be any real number such that nx is not greater than y for all natural numbers. This will be the negation in plain English. Okay. And then we have one more, the last one, 1.2.1. Let f from x to y be a function. Then when do you say that f is onto? For all y in y, there exists x in x such that f of x is equal to y. This is the basic definition of onto function. So how will you negate it? There is a point x in x such that for all x in x, f of x is not equal to y. That means there is a point y here in the codomain which does not have a preimage. So no matter which point you take, it is not going to y. It will go anywhere other than. So how will you frame the negation now in plain English? There exists a point x in x, okay, such that, sorry, there exists a point y in y such that f of x is not equal to y for all x in x. That means there is a point in the codomain which does not have a preimage. So that's the negation in plain English. Okay, so this completes this section 1.2. So in the next video, I'll jump to section 1.3, that is compound case.